glad to give this talk based on our latest work of this paper entitled Connections Between Graphs and Matrix Spaces. So my name is Chuanqi Zhang from the University of Technology, Sydney. I'm a PhD student, and this is a joint work with Yinan Li, who is a former state-of-the-art postdoc that you may know, Yuming Qiao, who's my advisor, and the Williamson family. So yeah, just a quick outline of today's talk. I will show you a quick introduction about matrix spaces at the very beginning, so you may see why we care about it. And our starting point is the existence of perfect matchings on bipartite graphs and the singularity of matrix spaces. So I will start there and show you a general framework of such connections. Actually, there is not only one correspondence between the properties of graphs and matrix spaces, but we also built the so-called inherited correspondence between the subgraphs and subspaces. We will see them later. Then I will introduce another example about the acyclicity on directed graphs and nilpotency of matrix spaces. And you can see that how it fits our general framework. At last, I will show some results with implications to other contexts, especially in quantum information theory. So here we go. Well, what is a matrix space? By the name, a matrix space is just a linear space spanned by matrices. And mathematically speaking, if you use this notation to denote the linear space of all n by n matrices over some field I, then a linear subspace I in this full matrix space is called a matrix space. So actually, we have a lot of representations for matrix space, and it's always convenient to specify a basis M1, M2 to MD for it. So in this case, S is the set of all linear combinations of M1, M2 to MD. And also, S corresponds to the symbolic matrix X1, M1 plus actual plus XD, MD. And here is a quick example. If we specify the two basis matrices as shown on the slide, and we use two variables to represent the matrix space, then represent the symbolic matrix, then you can see we got this result where the entries are all linear forms in the variables x1 and s2. So yeah. Oh, I think I unmuted myself. Yeah, you're muted, but speakers. Oh. Yeah, that works now. Yeah, today is still different. Okay, so sorry for that. Some technical issues can happen. Yeah. So yeah, let's continue. Yeah. So and try to see. Yeah, it works. Okay, so the matrix space S also corresponds to some superoperator defined in this way, where all the Troy cross operators are all consisting of the basis matrices. So in quantum information context, we mainly care about when the superoperator is a quantum channel. And yeah, we will see some examples later.
So will Mi star be a complex conjugate of Mi? The star denotes.
Yeah, the star means conjugate transpose. Exactly. Yes. Thanks for.
So then F is the complex numbers, or always?
No, actually, in our paper, we always consider a general field.
General.
Yeah, we don't have any restriction. But if it comes when it comes to the quantum information context,
Right. Yeah.
we consider complex field. Yeah. That's it.
Is normalized somehow? Because I guess you could take.
Yes, you're right. When it comes to the quantum channel, if this operator is a quantum channel, we need some normalization before this kind of stuff. Yeah. Thanks. So yeah, just so our main topic is about the connections between graphs and matrix spaces. So I'm going to show you how to construct matrix spaces from graphs. And here is just some common notations. We use n to denote integers from 1 to n. And for a pair ij in n by n, we define the elementary matrix as eij, where the ijth entry is 1 and all other entries are 0. So basically, there is a quick example. When we choose n equals 3, we say that e23 is defined in this form. So yeah. And in our paper and in this talk, we mainly care about the bipartite graphs and direct graphs. So I say that for bipartite graph G or direct graph G, the adjacency matrix is actually defined in terms of this elementary matrices, which is a summation over all the elementary matrices where the indices ij is generated from the H side. Yeah, so, and similarly, we define the graphical matrix space over some field I associated to G in this way. So it's not a single matrix anymore, but a linear span of all the elementary matrices corresponding to G. So here is something about the matrix space. And yeah, just another quick example to show you how to construct graphical matrix space from a graph. So given this bipartite graph, we can construct this graphical matrix space in this way. Since there is an edge between 1 and 2, so we just need to add a variable on the on the 1, 2 position. So, and just keep going, we can construct such a graphical matrix space. And our starting point is could be dating back to this theorem in the last century, which states that a bipartite graph G has a perfect matching if and only if its corresponding graphical matrix space has some invertible matrices. So, yeah.
You were considering directed graph, right? Because the even though the edges are not directed here, the matrix looks as if it's a directed.
Sorry, what do you mean?
Bipartite.
So yeah, what I'm talking about now is all about bipartite graphs.
That is the incidence matrix.
Yeah. Yeah. Yes. Yeah.
Okay.
Another questions? Yeah. So actually, this is not hard to see. So I'm going to show you the main ideas of this proof. And for the right direction, given that G has a perfect matching, we just take the matrix supporting on a perfect matching. So by supporting, I mean, we can look at this example. Yeah, given this perfect matching that I made in the red color, we can find the corresponding positions on the graphical matrix space, right? So they are actually C1, C2, and C3, if you look at the corresponding positions. And as long as we assign non-zero values to C1, C2, C3, we can get an invertible matrix. This is because of the special positions corresponding to the perfect matching. So yeah, for the other direction.
Why? It's not easy to see.
Do you mean why we can get a invertible
Why is
matrix?
this invertible? If you put the non-zero values there.
It's because
Determinant somehow?
yes. So basically, you can consider it as, so if you, well, simply speaking, if you cite C1, C2, and C3 as all 1, then you get a permutation matrix, right?
And you always get the permutation matrix if you do this for a perfect.
Exactly. Yeah. Okay, thanks. So for the other direction, we take the symbolic matrix of SG, as you may see, we turn it in this form. So given that SG has some invertible matrices, we can actually get that the determinant polynomial of this whole symbolic matrix is not identically equal to 0, right? And thereby, we can just ignore the sign of sigma, which is either 1 or -1. So thereby, there exists a product of monomials is not identically equal to 0 because it's just a term in the original determinant polynomial, right? So there must exist a term that's not identically equal to 0 for some sigma. And the point is that if we look into these terms, these monomials, then we can recover then we can recover perfect matching on the bipartite graph. So basically, x1, 2, x2, 3, and x3, 1 correspond to a perfect matching on the bipartite graph. So this is because sigma is a permutation. One can easily verify that. Are you happy with it?
Yeah.
Okay.
So you're getting all the monomials are permutations.
Yeah.
Okay.
Yeah. That's it. Yeah. So we can even have some further observations. So just consider this basic fact about perfect matching. Given bipartite graph G that doesn't contain any perfect matching, then there is an upper bound of the size of such bipartite graph, which is exactly n times n minus 1. So this is just a basic fact. And given the correspondence between the perfect matching and invertibility of matrix spaces, we can consider such a problem. So given a matrix space I's that doesn't contain any invertible matrix, how large can the dimension of I's be? So by comparison with the case on graphs, we claim that dimension I's equals n times n minus 1 is possible by this example. Basically, we just need to cite the last row of 0. So in this matrix space, there doesn't exist any invertible matrix, right? And we set all other variables. We set all other entries, free variables. So basically, this gives a dimension S equals n times n minus 1 matrix space. Yeah. And actually, there is a famous theorem by Dieudonn, first proposed by Dieudonn, stating that if matrix space I's doesn't contain any invertible matrix, then the upper bound of dimension of such matrix spaces is exactly n times n minus 1. So you can see there is another correspondence between the maximum size and the maximum dimension.
Is it easy to see or is it hard to prove?
I would say this one is hard to prove.
Yeah.
It requires some advanced algebraic techniques. Yeah. So let us just summarize our observations. So we found that G has no perfect matching if and only if the graphical matrix space SG has no invertible matrix. This is for any graph G. So we call it a basic correspondence between G and SG. And we also found that the maximum size of such G, by such G, I mean it has no perfect matching. Of course, G is a subgraph of the incomplete bipartite graph. The maximum size is equal to the maximum dimension of such matrix space. Of course, is in this full matrix space. So the point is that S doesn't have to be graphical, right? So this means that there are more subspaces in M and F than subgraphs of incomplete bipartite graph, right? So this is very amazing. And it's naturally to ask. Okay, so please know that M and F is also actually the graphical matrix of incomplete bipartite graph, right? So we can just replace M and F by S, K, and M. And it's natural to ask if we replace K and M with an arbitrary graph H, does it still hold? Yeah. So here is one of our main theorems, which states that for any bipartite graph H, the maximum size over all subgraphs of H with no perfect matching is equal to the maximum dimension over all subspaces of SH with no inverted matrix. So basically, you can see this still holds even if we replace a KNA by H. So of course, our theorem could generalize Dieudonn's theorem because we just need to take H as the n-complete bipartite graph. And I remember that Dieudonn was inspired by the applications in invariant theory, so which is a very different mathematical branch, but we provide a combinatorial explanation of this algebraic property, which is from the perspective of graphs. And I would say it's easier to see that upper bound from graphs, right? Yeah, so this is what we call as an inherited correspondence.
Sorry, is that your cursor over there, or otherwise I don't understand the symbol there with the S?
Is the
Yeah.
Sorry for that. Yeah, it's not SI. Yeah, okay. Let's continue. So yeah, here I'm going to show you our general framework given the previous examples, right? So basically, a basic correspondence is a result of this form. For any graph G, G satisfies some graph, the right property P, if and only if SG satisfies some linear algebraic property Q. And we can boost the basic correspondence to the so-called inherited correspondence. That's for any graph H, the maximum size over all the subgraphs of H satisfying P is equal to the maximum dimension over all the subspaces of SH satisfying Q. And as you may see, the basic correspondence immediately implies the less equal result. Why? So given a maximum subgraph satisfying P, by the basic correspondence, we can immediately get that its graphical matrix space satisfies Q, right? But it doesn't have to be the maximum one over all the subspaces in SH satisfying Q, right? So this is why I say the basic correspondence immediately implies the less equal result. And as I mentioned, the other direction requires more advanced techniques. So let's take an example. Actually, we can boost the result on the last slide into this result. So it states that G has no matching of set R if and only if every matrix in SG has rank less than R. And we also found the inherited correspondence for that. That's for any bipartite graph H, the maximum size over all subgraphs of H with no matching of set R is equal to the maximum dimension over all subspaces of SH where every matrix has rank less than R. So basically, with no matching of set R corresponds to the property P I mentioned above. And where every matrix has rank less than R corresponds to the property Q that I mentioned above. Yeah, here it is. And as I said, the proof idea of larger equal part is based on Mashulam's proof of Dieudonn's theorem. So basically, you can see it requires more advanced techniques. Okay. Any questions so far? Yeah.
Is there because as you say that the graph and it just I mean I just more for the previous result that that S doesn't have to be a graphical.
Okay. So do you mean?
No, I mean the one just from just now. On the next slide. But no, sorry. Oh, wait. Yeah. But is it the case that I mean if you consider like a weighted graph, do you get some kind of correspondence there? With the existence of inverse elements in H space.
Yeah, so What do we mean by the weights? You mean?
Oh, because presumably, because right now all of the graph matrix spaces are limited to a certain form, right? You cannot write every matrix space as a graph matrix space.
Yes.
But you could presumably, if you consider weighted graphs, you could write any matrix space as a graph matrix space.
I'm not sure about what you're talking about.
I
Okay.
think the correspondence between combinatorial properties and algebraic properties, right? So you look at sizes of matchings and ranks. Whereas if you now instead look
Which
at
doesn't
weights
really
of
make sense.
matchings or something, maybe you want to replace the rank with something analytical. So you can
Yeah, you could have something like, I don't know, like preference matchings where one edge has a larger weight than the other, and then you can express anything, but then you can express, let's say, real numbers, but
Yeah.
complex numbers would be quite hard to interpret.
Yeah. Thanks. I learned a lot.
So the S of H is the matrix subspaces based on a graph. Do I recall correctly that the graph determines the supports of these of the matrices in, say, S of H or S of G?
Mhm.
So say if you have a graph G, then S of G has matrices whose supports are limited to the edges of G, right?
Yeah.
Right. So
Yeah.
what I recall from Schulam's work is that when he looked at maximal ranks and matrix subspaces, what mattered not so much the supports, but the lexicographically
Yeah.
first non-zero
Yeah,
elements,
yeah.
bases.
Yeah.
So he would allow support outside of the edge set in a sense and still get.
Yes, but yeah. Well, this is about our proof details. I remember what you said, but yeah. So yeah, I need to think about it more by looking into our paper. So yes, basically, for the editor of this proof, we need to, for given matrix space, for given subspace in SH, we need to construct a subgraph supporting on that subspace, right? So that's what we need to find, and and such subgraph should have some requirement about size or something.
I'm suggesting that you can have these correspondences in a setting where you replace SG with a larger set, where for every edge you have a matrix functioning as a basis, where that edge is the lexicographically first non-zero coordinate of your matrix.
Yeah.
It doesn't have to be zero.
Yeah.
Allow more non-zero.
Yeah. I'll think about it more. Okay. Yeah. Thanks. Let's continue. So yeah, here I showed you a general framework of our work. So let's take a look at another example about the connection between acyclicity on direct graphs and nilpotency of matrix spaces. So let's see how it fits our framework. Before the content, I'm going to show you some definitions as preliminaries. So the graph is acyclic if it has no cycles, and the matrix B is nilpotent if there exists a power such that B raising to that power could reach 0. And there is a basic fact regarding the adjacency matrix, which is a direct graph G is acyclic if and only if its adjacency matrix AG is nilpotent. However, this doesn't hold over any field. Like this doesn't hold over the field of order 2. For example, if we take this 2 complete directed graph, which means it has 2 subloops and it's not acyclic, but we take the matrix multiplication of the adjacency matrix twice, yeah, so it would give a 0, which means it's nilpotent. And we want to do something similar on matrix spaces. So we define a matrix space S to be nil if any matrix in this matrix space is nilpotent. And we got this basic correspondence between graphs and matrix spaces. That a direct graph G is acyclic if and only if its graphical matrix space SG is nil.
Sorry, what is nilpotent? Like, when is a matrix nilpotent?
Sorry, do you mean the intuition of being nilpotent?
No, I mean, when would we call a matrix nilpotent? I don't know what the definition of nilpotent is.
So the second line.
Ah, okay. Sorry. Yeah, thank you. Yes.
Yeah.
And that's an example.
Yeah. Okay, thanks. And surprisingly, our observation holds over any field. So this holds over any field, which is the P. And again, we consider this basic fact about directed acyclic graphs. Given a directed graph G that doesn't contain any cycles, then the upper bound of its size is interest 2. And we can consider the corresponding problem on matrix spaces. So given matrix space is nil, how large can dimension S be? And we can see that dimension i's equals interest 2 is possible by this example, because any upper triangular matrix is nilpotent. This is just a basic fact. And we just set all the entries above the diagonal free variables. So this gives you interest 2 dimension matrix space. Yeah. The point is that Gerstenhaber gave this beautiful theorem stating that if a matrix space S is nil, then the upper bound of the dimension of such matrix space is interest 2 exactly. So actually, Gerstenhaber, I remember that in Gerstenhaber's proof, his proof requires a large sufficiency field, while Siritskin removed this restriction on the field. So now we have this kind of stuff works over any field. Yeah, so now let's put it into our general framework. So a basic correspondence between them is G is acyclic if and only if SG is nil. And an inherited correspondence is that for any directed graph H, okay, so we are wondering if the maximum size of subgraphs G of H being acyclic is equal to the maximum dimension of subspaces of SH being nil. And fortunately, we found it. So this is our one of our main theorems stating that for any direct graph H, this actually holds. Yeah, and as we see, this generalizes Gerstenhaber's theorem because we can just set H as the complete direct graph. And regarding the proof, we adapt Posit's proof of Gerstenhaber's theorem to prove the relatively difficult direction. And there is a straightforward corollary stating that given a matrix space S, it is NP hard to determine the maximum dimension of new subspaces of S. This is directly derived by the case on graphs. So yeah, here's the thing. Any questions?
Quantum channels where the Krauss operators are nil.
Yeah, this is a good question. I haven't thought about it before. But we'll see some other examples regarding quantum channels soon. So maybe.
I want them to sum them to the some dagger to the identity.
Right. So that's not possible.
And maybe.
Yeah, very interesting question. Yeah.
Yeah, I just have one general question. So you were mentioning on this previous slides, if you have if your elements of your matrix are essentially elements of Z2, then you had this example where you have these two by two matrices with just ones. You multiply them, you get a matrix with all zeros. Not this one, but on the previous slide. Over here, yeah. So would this be? It seems that this should be related to, let's say, fermions flopping around on the graph. Is that correct? Or is that?
Yes, exactly.
Yeah.
Yes. So generally, if we don't take the field of order 2, if we just take it over real field, we can, it's about the length of the path on graphs when you take the power. So,
Sorry, could you repeat that?
yeah, let me make it clear. I think we can add some examples.
Yeah, if it's not important for the remainder of your talk, so fine to just leave.
Yeah. It's right, and it's included in our paper. So if you are interested in, I suggest you, look into our paper.
Right.
Yeah, thanks. Yeah. So, let's just take a break and make a quick summary. So our basic correspondence is a result of this form. P satisfies P if and only if SG satisfies Q. And inherited correspondence generalizes the basic correspondence to this form, which is about the maximum size and the maximum dimension. Actually, we also have other results that could fit in this framework, like the strong connectivity of direct graphs and irreducibility of matrix spaces, and isomorphism between graphs and congruency or congruence between matrix spaces. I'm not going to cover them all in this talk because we can just talk something different, especially in quantum information context. So actually, such connections are not only found for graphs and matrix spaces, but graphs and other objects. Like we can consider the so-called graphical quantum channels. Yeah. So this is some previous works on graphical quantum channels. And this construction was first given by York and others in this paper. I will call this paper as BBIOM because I'll just mention it again and again soon. This is an important citation in our paper. Yeah. So what's the construction? That's for every matrix X, the graphical quantum channel sends X to this form, where, as on one side, there is a normalization factor y 1 over d. Know that we care about the d regular graphs. So d is here, And the Troy cross operators are all consisting of elementary matrices generated by the edge side of G. So basically, it's the so-called graphical quantum channel. And the thing is that BBLI gave this beautiful theorem, which is actually a corollary to their proposition 3.7, stating that for Rayleigh, the regular graph G, the spectral expansion of G equals the spectral expansion of YG. So when it comes to the spectral expansion of a graph, it's basically the second largest absolute value of these eigenvalues of the adjacency matrix. And when it comes to the spectral expansion of a superoperator, of course, we can define something very similar about the eigenvalues for the superoperators. Yeah. So it's again the second largest absolute value of these eigenvalues. So
could you repeat what a spectral expansion is?
Sorry?
Could you say again what a spectral expansion is?
The spectral expansion, you can treat it as the second largest absolute value of its eigenvalues. So basically, you enumerate all the eigenvalues and make absolute values of them, and you take the second largest one. Because
okay, and then you're assuming the first one is 0 or so.
the first one would be 1.
Okay.
Yeah.
It's like a Markov chain.
Yeah.
Okay. And then the second largest eigenvalue tells you if you do it a whole bunch of times, how quickly it sort of converges. Oh, right. Yeah, I see.
Yeah. Thanks. Just a quick recap about this definition of being irreducibly covariant. So a quantum channel is irreducibly covariant if there exists a compact group gamma and a continuous irreducible unitary representation such that these conditions hold. Yeah, so the reason I recall this is for this theorem, which states that the D-regular graph G is vertex-transitive if and only if its graphical quantum channel phi G is irreducibly covariant. So just show you this conclusion. And the point is that we can also consider vertex transitivity in our setting, right? Which is about matrix space setting. Yeah. So just a recap of the definition about vertex transitivity. Again, we consider the directed graphs and we let this notation to be the automorphism group of G. G is vertex transitive if and only if automorphism group of G is transitive. And this is just an example for vertex transitive graphs. Basically, after rotation, you can get the same graph. Yeah, so just give you some indication. And regarding the matrix space wise, we recall the definitions for conjugacy or congruence reducibility. So before that, let's take a matrix group G in the general linear group and take a vector space U. So we say that G is reducible if there exists a non-zero and proper U such that for any matrix in this matrix group G, A acting on U is still in U. Otherwise, we call G irreducible. And in this case, of AU still in U, U is called an invariant subspace. So being reducible basically means it admits non-trivial invariant subspace. So just some wordy definitions. And yeah, we mainly care about the matrix space stuff. So here we take matrix space I's and we define conjugacy of I's in this form, which is a collection of such invertible matrices that S could be preserved by the conjugacy action of T. So clearly, conjugacy of I's is a subgroup of general linear group. And we see that S is conjugacy reducible if conjugacy of I's is irreducible as a matrix group. So here you may be wondering the difference between a matrix group and matrix space. So basically, when it comes to matrix space, we care about the linear span, we care about the addition operation, right? But when it comes to a matrix group, the operation changes to the matrix multiplication. And this is just a good example to show you why. Because given two matrices in this matrix group, T1 and T2, we cannot say T1 plus T2 is still in conjugacy of S, right? We don't know this. But we know T1 times T2 is still in this matrix group. We just need to apply the preservation twice to get this result. Yeah, so similarly, we can define a matrix space being congruence irreducible by simply replacing inverse with transpose. So the other things follow the same line. Yeah. So given these definitions and notation, we can say that we found that G is vertex transitive if and only if congruency of SG is reducible, if and only if congruence of SG is reducible. And for the first two, for the equivalence between the first two is proved in BBLIM. So we basically can get such implication to their result. So yeah, these equivalencies are found by us. And basically, yeah, just to give you some intuition about the relationship between the two notions. So basically, in our setting, we kind of generalize the unitary representation of when it comes to being irreducibly covariant. I mean, we take the general linear group. So basically, given our equivalence we can easily get from point 2 to point 3, because point 2 basically means there exists an irreducible subgroup in conjugacy as G. If you write down everything, you'll find this. So basically, a subgroup being irreducible could imply the original, the whole group being irreducible. So basically, we can easily get point 3 from point 2. So yeah, just give you some ideas about that. So yeah, I'm going to talk about some further work by us. This is not by us, of course. This is also, we're also inspired by the work from BBLIM, which states that for any deregular graph G, the spectral expansion of G equals the spectral expansion of phi G. I recall this. And inspired by this work, we investigated the linear algebraic expanders generalized from graphs in this follow-up paper. So we can get such a result, which is quite similar to the one in BBLIM, which states that for any undirected graph G, G doesn't have to be deregular. The vertex expansion of G equals the dimension expansion of the graphical matrix tuple BG. So let me explain it more clearly. So yeah, for undirected graph G, the vertex expansion of G is defined in this way. It's basically a minimum of a fraction where where partial out W means the vertices outside W connecting with the vertices in W. So basically, it's doing the counting. And a mesh tuple is basically a bunch of matrices. And we define a mesh tuple acting on a vector space in this way. It's basically you take every matrix acting on the vector space V and then take a linear span of all the results. So the dimension expansion of B is defined as this pi, which is again a minimum of a fraction. So you may be wondering the intuition to define such a notion. So let me give you why it's defined in this way. Yeah, we can define the graphical matrix tuple of G in this way, which is not surprising. And we consider when V is a coordinate subspace, such as V could be spanned by the standard basis E2 and E3. So in this case, V is treated as a vertex subset 2 and 3. So basically, dimension V is the same as the size of W in some sense. And there is a basic fact about the elementary matrices. That's when we take an elementary matrix acting on a standard basis, then if and only if K is J, we can get a non-zero result. So therefore, if you think about it more, you can see that basically dimension V plus BV is doing the counting for the vertices connecting with the vertices inside V, and we subtract dimension V to recover the definition of partial out W. Yeah, and this is what I showed you before, which is our main theorem. For any undirected graph G, the vertex expansion of G is equal to the dimension expansion of the graphical matrix tuple. And the proof is based on the ideas of other words. So yeah, I'm going to just show you some further work at the end. So in the classical setting, we know that all three expansions are equivalent, which means a graph is vertex expander if and only if it's edge expander and only if it's spectral expander. However, this is not the case for linear algebra expanders. And we found that constant degree quantum expanders are always dimension expanders. However, there are some dimension expanders that are not quantum expanders. So yeah, this is the work in another paper, not in this matrix space paper. Yeah, so here's the end of my talk. Just a quick summary of everything. The basic correspondence is this form, G satisfies P, finally if SG satisfies Q, and inherited correspondence is in this form. From sides over all the subgraphs G of H satisfying P is equal to the maximum dimension over all the subspaces of SH satisfying Q. And the point is that from a graph G, we can construct not only graphical matrix space SG, but also graphical control channel YG, or graphical matrix tuple BG, possibly even in other contexts. And then we establish connections between them. This is how we conduct research. Thanks so much.